So today we are going to discuss the complements of a function. So far we have learned about how to solve the Boolean functions using Boolean algebra. We have different types of postulates. Some of there are laws, some of there are theorems. With the help of these theorems, we can minimize our Boolean function, and so that the implementation of the Boolean function can be simplified. So there is another way in many cases we need a complement of a function. Function is in your Boolean expression. It may be in terms of and, or, and not variables. When as in case of, we can take the complement of a number. In complement, when we are talking about binary number, zero is complement of 0 is 1 and complement of 1 is 0. In the same manner, we can take complement of the functions. And why it is needed in a real implementation? Sometimes the complement of a function is needed. So where there is such requirement, we have to take the complement of function, and it is nothing but can be done with the help of the De Morgan's theorem. Suppose we have a function f equals to x bar y z bar plus x bar y bar z. This is a Boolean function which is given to you, and you have to take its complement. Then bar is a complement. We write like f equals to x bar y z bar plus x bar y bar z. That is the given Boolean function, and we have to take its complement. Now the complement is taken, then we write f. The complement of f will be f bar, that is the NOT gate, and we have x bar y z bar or x bar y bar z whole complement. We have put it complement both sides. Now when we solve it further using the De Morgan's theorem, and De Morgan's theorem says that break the line, change the sign. So applying this theorem onto this, we have x bar y bar z bar whole bar. We have break line from here. Then again x bar y bar z whole bar, x bar y bar z whole bar. So this is the first breaking of the line. We have applied De Morgan's theorem here. Now again we have applied De Morgan's theorem to the first. For the first bracket, we have applied the De Morgan's theorem, and it comes to be x bar again bar. This AND gate will be replaced by OR gate, or y bar, and again OR. This is your AND. The AND is replaced by OR. Then Z bar again bar. So x bar double bar will be equals to x. Z double bar will be equals to Z. Similarly here again. So there was some technical issue, and let us start from the beginning. Now we have to take the complement of y, then y is given by x bar y z bar or x bar y bar z. So what we do, we put complement on both sides. Here f is f bar, then we have the complement of this whole function, and this is x bar y z bar or x bar y bar z whole complement. And this complement is solved with the help of De Morgan's theorem. And De Morgan's theorem in general, yes.
सर एक बार मीटिंग अनलॉक कर लो.
अच्छा मीटिंग लॉक हो गई. ओके ओके फाइन, जस्ट अ मोमेंट. नहीं मीटिंग तो अनलॉक है अभी.
Okay, sir.
Okay, fine. So we have to just break this. In general, we have to break the line where there is two variables, and we have to change the sign. And sign is changed in such a way that and is converted to or, and or is converted to and. Now here is the next step. We have break line from here. So we have two terms. This sign will be replaced by AND gate. The OR is replaced by AND. We have X bar, Y, Z bar, whole bar, then X bar, Y bar, Z, whole bar. Now again, we have to solve this complement, and this complement is solved in such a way that X bar, whole bar, X bar, double bar, and this AND is converted to OR, then Y bar, Z bar, or is already, then double bar, it will be converted to Z. Again here X bar, double bar, or Y bar, double bar, and this AND is replaced by OR and Z bar. Now in this way, this term F, which is which bar X bar, Y, Z bar, or X bar, Y bar, Z, is converted to in complement form X or Y bar or Z, or X or and X or Y or Z bar. And in both case, you can implement both the Boolean function with the help of AND gate, OR gate, and the NOT gate. When we'll design the combinational circuits in the upcoming units, then we will need to implement, or we need to take the complement of a function. Then you will better understand what is the need of taking a complement. Now, as we have discussed the Boolean functional simplification in the last lecture, we can take another example. Then we'll be better to understand what's the need of simplification of Boolean algebra. A simplified Boolean expression uses the fewest gates possible to implement a given expression. There is always a need when you are designing a digital circuit, then the cost must be less and it should be simple. Means complexity should be minimized. So in such a way, when we are given a specifications, then I have to design this type of circuit. This number of inputs are there. This number of outputs are there, and it should behave like this. If the input is this, then the output will be this. So in such a way, what we do, we develop an algorithm and we design, we come a whole design and find out some Boolean expressions. Now we have to minimize these Boolean expression to implement that particular circuit. So in that case, we have to simplify the Boolean function, and the very first method to simplify the Boolean function is with the help of Boolean algebra. So here let us say this is a circuit, and it is given by if we have to find out what is the output. Here is A, here is B, then the output of this particular gate is A and B. Then again, at this gate is A, and next output is B or C. Then the output will be A and B or C. B or C, B or C is coming from this output. Now the output of this third gate is, here is B or C and B, and all three outputs will be combined with the OR gate, and the expression comes in such a way. We get AB from this gate, A, B or C from second gate, A, B or C, and this is B and B or C. So in such a way, we can find out the output of any circuit. If you are given any circuit, then you can find out what will be the Boolean expression of that particular circuit. Suppose this is the expression what we have got from the last design, and we have to simplify it with the help of Boolean algebra. Now, step by step, whatever postulates and laws we have studied in the last lecture, we'll apply it one by one, and they'll find out that is it possible to minimize it or not. Now, I suppose that all of you please solve this question in your notebook, so that it will be easier with step by step we can find a solution. Now, with the first step, what we do, we do the distributive property. Means whatever are the terms in the bracket, we multiply. Then the first term is AB, next term is AB, next term is AC, next term is B and B, Next term is B and C. We have just opened the brackets and we have find out some expressions. Is that correct?
Yes, sir.
Okay, fine. Now the next step, we apply the property rule 7. B and B is B. We have written the A and A is A. So here in this case, B and B will be replaced by B. Similarly, we have two terms, AB or AB. So I can say it X or X equals to X. So in the next step, I can minimize rule 5, AB or AB equals to AB. So this expression is minimized to AB. These two terms are combined, then AC or B or BC. Now we'll see the further if we can minimize this expression. So with the rule number 10, we have B plus BC equals to B. So what I can here, I can take B from the last two terms. So B is common, it comes 1 plus C and 1 plus C is 1. So it comes B and 1 and B and 1 is B. So this B plus BC equals to B. Now again we'll look that if we further we can solve this. Yes, with the rule number 10, AB plus B. If I take B common, then it comes to A or B, A or 1 and B. Then it A or 1 is 1 and B is B. So this total term reduce from there here. Initially it was AB plus A and B or C, or B and B or C. It is replaced to B or AC. Now when we compare the circuit here, this was your initial circuit, and after simplification we have reduced to like this, B or A and C. So you can directly see that after the simplification we have reduced the number of gates. Here the number of gates are 1, 2, 3, 4, 5, and we have reduced it to the only 2 gates. Further, the cross connections and the wiring has been very much simple when we have simplified the Boolean algebra, Boolean function with the help of Boolean algebra. So this is the way that how we can minimize Boolean function, Boolean algebra, Boolean function, and we can minimize the number of gates, hence the cost and hence the complexity. So both can be reduced. And this is always a big challenge when we are designing a circuit. When we are going to buy a mobile, you will look that it should be pretty much attractive in the design. It have much more features and it should cost less. So the cost less comes when we have a simplified implementation of the digital circuit. Now these are the some questions that you can try in at your home. So write down these questions for the practice. The first expression is A B bar and C or B D, or A bar B bar and C. So you just write these question in your copy and then you can be able to solve it with the help of Boolean algebra. What you have to do, you just write your all the postulates in one side, then you, find out that whichever postulates can be implemented in any of the two terms, 3 terms. Then you, when you combine these terms, you will be getting some feasible answer. So in this case, let me clear. Then first, what you do, you open this bracket, then it will be A B bar C. Multiply then to the A B bar B D. Then open this so large bracket. Then multiply whole terms by C. So with the hence you will get an expression without any bracket. Then solve it. Either which postulate can be applied to a any literal. Another example you can write down is A bar BC plus A B bar C bar plus A B bar C bar plus A B bar C plus A B C. Try to solve this question, and the last question is AB or AC complement plus A bar B bar C bar. So these are the 3 questions you can try at home for the practice. If anyone of you found any difficulty solving this, then you can contact me. Then I'll help out you that how to solve these. It may be possible that the number answers may differ. and it depends that which number of postulate you are applying first. Now come to the another topic, and that is pretty much important, and then after this we'll move to the combination circuits and solving the K-map and all. Standard form of Boolean expression. So far we have term whatever here was, these all are called Boolean functions. This is A, B bar and C, or or plus A bar, B bar and C. This is called as Boolean function. So there are three different Boolean functions. So we have to represent the Boolean expression or Boolean functions with the help of standard form. So first we look at what the standard form stands for. All Boolean expression, regardless of their form, can be converted into either of two standard form. So to represent any Boolean function, there is only two types of standard form, and which are as the sum of products, that is called SOP, and the product of sums, that is called POS. So any digital function, any digital circuit is defined by a Boolean function or Boolean expression, and which is of two types: sum of product, POSOP, and a product of sum, that is POS. Now we'll discuss one by one what it stands for. The standardization makes the evaluation, simplification, and implementation of Boolean expressions much more systematic and easier. So in general, there are SOP and POS. Then we have standard form of SOP and POS. Now the canonical forms, that is the min terms and the max terms. So with any number of variables, suppose we have three variables x, y, z, and with these three variables we will be having 8 number of combination. Number of inputs are 3, x, y, z. Then the number of combination will be 2 raised to power 3, that is 8, and it will range from 0 to 7. So it starts from 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 1, 1, 1, 0, and 1, 1, 1. So let us first discuss what the min terms mean. Min terms are the product terms. So we write 0 stands for complement. If the input is x, then 0 stands for x bar. For the y, 0 stands for y bar, and for z, 0 stands for z bar. So the min terms are represented as AND terms. So I have written here the AND term or the product term. So I write 0, 0, 0 means it is x bar and y bar and z bar. Suppose it is 1, 1, 1. The 1 stands for without complement. That means x and y and z. So these are the terms. So for the 0, 0, 1, I have write x bar, y bar, z, because z is 1. So I have written as z. X is 0, I have written as x bar. Suppose 1, 0, 0. So x is 1. So it is x, y bar, z bar. And the designation of these min terms are, this 0 is represented small m, subscript 0, m0. This value is 0, 0, 1, stands for 1. It will be m1. 0, 1, 1 stands for 3. Then the min term designation will be m3. Here 1, 0, 1 stands for 5. And expression is x, y bar, z. It will be represented as m5. 1, 1, 1 stands for 7. And the min term is x, y, z. And the designation will be m7. So all product terms are known as min terms. Now come to the max terms. Max terms are the OR term, or we say, suppose it is it is just opposite to the min terms. If I take complement of min term, then it will be a max term. So if I take complement x bar and y bar and z bar whole bar, then it comes to be x double bar or y double bar or z double bar or, and x double bar is nothing but x or y or z. So the max terms and min terms are both complement of each one. So if I say that is for the 7, the min term is x, y, z, then I'll take complement of this, then it will be x bar or y bar or z bar. So here written here a, and the designation of the min terms or the max terms are in the capital form, that is m capital 0, m1, m2, m3. This subscript is the weight of the number. 000 stands for 0, so m0, and it is in the max term it will be written as x or y or z. In terms of min terms, it will be written as x bar, y bar, z bar. So these are the two standard canonical form representation of any Boolean expression, min terms and in terms of min terms and the max terms. So keep in mind that min terms are always product term, main terms are all sum terms. So here are the sum terms, x plus y plus z. Now let us discuss in detail what the SOP stands for. The standard form, sum of product form. An SOP expression when two or more product terms are summed by Boolean addition. Means we have different two and more product terms and they are summed. Then it is called sum of product. So actual term is min term. Product is the min term. So for an example, let us say AB or ABC. So AB is a product term. ABC is a product term. Again, ABC or CDE or B bar, C, D bar. So there are three product term and these all are summed. That hence it comes sum of product. The product terms are summed. Then it is called SOP. In the last expression, we have A bar B plus A bar B C bar plus AC. So this AC, A bar B, C bar, A bar B, these are the product term, and when these product terms are summed, then it is known as sum of product. Also like this, A in this we can say it is a product of A and 1. A and 1 is A, so A or B bars, A bar, B bar, C, or B, C, D bar. So these all are known as sum of products. In an SOP form, a single overbar cannot extend over more than one variable. Means when we are complementing, or so then it should not be more than two variables. However, more than one variable in a term can have an overbar, and that can be just understood by this. So we have here A bar, B bar, C bar. This is the right product term, and we cannot write a b c whole bar. This is not a product term, because when I open this bar, then it will be A bar or B bar or C bar. So in the SOP it should be kept in mind that the complement should never be of the whole term. It can be of different variables. It can be A bar, B bar, C bar, but it can never be A, B, C whole bar. So because when we open this whole bar, it will be a sum term. Now, how to implement of the SOP? Suppose we have AB plus BCD plus AC. So this is a sum of product term, and I have to implement it with the help of gates. So for the and or implementation, because the product term is obtained with the help of and these are summed with the help of or gate. So we say it is and or implementation. So here is the implementation. A and B first AND gate, B C D second AND gate, AC is the third AND gate, and we have a 3-input OR gate which will add all three product terms. So here X is nothing but X is a sum of product. This sum is done with the help of OR gate, and the product is done with the help of AND gate. Further, we can implement with the NAND implementation also. It will be like this. So how this implementation comes, I will study later on that how to implement any Boolean function with the help of NAND gate only, because NAND and NOR both are the universal gates. We'll discuss this later on that what it stands for. So up to now we are stick to this particular implementation, that is AND OR implementation. So the all product terms are obtained with the help of AND term, and or some products are implemented with the help of OR term or OR gate. Now general expression of the sum of product. Any logic expression can be changed into SOP, that is sum of product form, by applying Boolean algebra technique. For an example, suppose we have A and B or CD. So what we do, we just open it with the help of the Boolean postulates. Then we multiply A into B, AB. Then we multiply A into next term ACD. So this term is your sum of product. This is not sum of product. This term is your sum of product. Now again we have further example. Suppose AB or B, C, D or E, F. So what we do, we just expand it and we'll get the sum of product. So first term is AB, right? Then we have B, C, D next term, then B, E, F. That is the next term. So this is called sum of product. Again, some term. So what we can do with this help, just in the mathematics, you have done multiplication. First multiply all the these B, C, D by A, then OR it and then multiply by B by B, C, D. So first term comes AB, next term come AC, next term come AD, next terms come BB. So we can write it like just B. Next terms B into C, next term is B into D. So this is called a sum of product. Now, in this case, we have a whole complement. So that a whole complement cannot be a sum of product. So what we do, we open this complement. So when we open this complement between these two terms, then we break the line. Sign is OR. It is converted to AND. So we get C bar, A or B bar already. Then again bar. So we get A or B and C. Then again we multiply it A C bar or B C bar. These are the, hence we can get the sum of product by applying Boolean algebra technique. Now let us discuss what the standard sum of product means. And one question will be there in your examination about to convert into the standard form of operation, standard SOP, standard POS. So here is the first. Let us discuss what the standard SOP form means and how to convert a Boolean function into a standard form of SOP. And standard SOP expression is one in which all the variables in the domain appears in each product term in the expression. Suppose let us discuss here. It will be tough to understand. Now here we say that the variables are A, B, C, D. But in the first term, C and D are missing, and in the second term, B is missing. So standard form says that when we have four input variables A, B, C, D, then each product term, each variable must appear. If it does not appear in each terms, then it is a general expression. When both the terms have four variables, then it is known as standard form of SOP. That I was trying to explain here in this statement. A standard SOP expression is one in which all the variables in the domain appear in each product term in the expression. Now, this is an example. We have four input variables A, B, C, D, and we have three product terms, and all three product terms have all the four variables either in the true form or in the complemented form. So here we have A, B bar, C, D, or A bar, B bar, C, D bar, or A, B, C bar, D bar. So this is the way how to represent a Boolean function with the help of standard form. Now, the standard SOP expressions are important for constructing truth table when you implement the circuits, and the Karnoff or K-map simplification method when we have to simplify a Boolean function with the help of Karnaugh map or K map, then it is very much helpful. Now, suppose we are given a general a standard sum of product, and we have to convert it into standard SOP. This will be the first very first step when we are using going to when we are going to simplify the Boolean function with the help of K map. So in every time we have to convert it into SOP. So let us discuss what is the process to convert into the SOP. Now, the very much first step is multiply each non-standard product term by a term made up of the sum of a missing variable and its complement. This results in two product terms. When we do an example, then it will be easy to understand. Now, as you know, you can multiply anything by 1 without changing its value. If I multiply x by 1, so it is x and 1 is equals to x. And this 1 can be y plus y bar. So here we are saying that y plus y bar is 1 and it is multiplied by x. Then the value will be, if y is missing, then we will get x and y both in the terms. When we come to the example, then it will be pretty much clear. Now, in the second step, repeat step 1 until all resulting product terms contains all variables in the domain in either complemented or uncomplemented form. Now, in converting a product term to standard form, the member of the product term is doubled for each missing variables. Now, let us come to an example. Suppose we have to convert the given Boolean expression into standard SOP, and the Boolean function is a b bar c or a bar b bar or a b c bar d bar. So when we look into the expression, we have three input variables a, b, c and d. Now when we look at the each term, this term has four variables a, b, c, d. This term has only two variables, that means c and d are missing. And this term has only three variables, that means d is missing. So let us solve one by one. Let us take the first term. First term is a b bar c. So what I do, I multiply it by d or d bar. D or d bar is nothing but 1. So I multiply by this term by 1 and I get a b bar c d or a b bar c d bar. So this one term is converted into two terms, and these both terms are standard form of SOP because all the both terms have all four variables. Now let us see the second term a bar b bar. So a bar b bar has two missing terms. So we have to multiply it by two terms. So first I do a bar b bar. So I multiplied by c and c bar because c is missing. So I came a bar b bar c or a bar b bar c bar. Just multiply. Then these terms a bar, these both terms has missing d variable. So what we do, we again multiply by d and d bar. So this term is again multiplied d and d bar, and this term is again multiplied d and d bar. So I get a bar b bar c d or a bar b bar c d bar or a bar b bar c bar d or a bar b bar c bar d bar. So when we look into these four terms, all the four terms have all four input variable. So we can combine the expression, and now the expression becomes this general standard form or general sum of product is converted into the first term is this term is replaced by a this term a b bar c d or a b bar c bar d bar. Second term is replaced by this. So these are four terms, and last term is completely in the form of standard SOP this. So when we have only three input variables, sorry, three input product terms, here we have 1 2 4 6 and 7. We have 7 product terms. So in this way you can convert any general sum of product into standard form of SOP. So I think we'll discuss the next topic, the binary representation of SOP in the next lecture.
Okay, sir.
If you have any